Warning, the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is meant for those students who've already gone through elementary and intermediate algebra and are on their way to a calculus course. And we're just reviewing how to simplify compound rational expressions. Now, to be very honest with you, I have a lot of videos on this specific topic, mainly because it's that important for students going into calculus. You have to simplify compound rational expressions quite a bit. But this one is specifically intended for those students who've already gone through college algebra. So this is for those who are now in pre-calculus and you've seen some high-level algebra already. So let's go ahead and review this topic. A compound rational expression is basically a fraction containing fractions. Officially, it's any rational expression that involves other rational expressions, which I will call each of those other rational expressions sub-rational expressions. For an example, if you consider the rational expression, it could be anything really, but let's just make up something like 1 over the sine of x plus 2 minus 1 over the sine of x minus 1 all over. So notice that that presents us with a bunch of fractions in the numerator of a larger fraction. And let's pretend that the larger fraction is 11 over, I don't care, the cosine of x plus let's just say 17 over the square root of x or some silliness like that. Now that's actually something you'll never face, but it still gets the point across that each of these fractions I'm going to call sub-rational expressions or sub-fractions. That's important to know as we move forward. Now, since you've already gone through algebra and you've already gone through college algebra, this is just a reminder of all that stuff. By the way, it's also assumed that you've had a trig course, and so I'm now allowed to do compound rational expressions that involve trig functions. So at this point, you should pretty much recall how to simplify compound rational expressions, so I'm not going to have to write down a method here. Instead, I'm going to showcase the method. So simplify this compound rational expression. Now, this may not look like a compound rational expression to you, but it actually is. If you think about it, those negative exponents just mean that whatever they're attached to can be written as 1 over that argument raised to the second power. So that is, this sine of theta here can be written as 1 over the sine of theta and quantity squared. And the next one can be written as 1 over the cosine of theta being squared. Now, since you've had trig, then you know that this is a silly way to write these. So instead, I'm going to write this as sine squared of theta, and the other one I'll write as the cosine, again, squared of theta. And now we have the denominator. The denominator is going to be 1 over, again, the sine squared of theta. And now we have minus 1 over the cosine squared of theta. Definitely a compound rational expression. It has fractions within this fraction. The goal here is to multiply both numerator and denominator of this compound rational expression by the LCD of all the minor fractions within it. That is, you're going to look through all these little sub-fractions, look at each of their denominators, and you're going to create an LCD out of those. So here we go. Let's go ahead and write that down. And I'll write that off to the right-hand side. I'll just go ahead and list out that the LCD here is going to be the sine squared, because one of our denominators at least has a sine squared. And then we're also going to say we need a cosine squared, again, because one of our denominators has a cosine squared, specifically this guy and this guy. So both of those denominators we've already considered And both of these denominators we've also considered. So now we're going to go ahead and multiply both numerator and denominator by that LCD. To make our lives a little bit easier, I'm just going to write it this way. We're going to group up that entire numerator and just write LCD and LCD. This just means we're multiplying by LCD over LCD, which is just 1. So you're not really changing the value of this fraction, you're just changing the look of this fraction. And now we distribute that LCD to each of the terms in the numerator and to each of the terms in the denominator. Let's go ahead and do that. And that you should be okay with just because you know how to multiply through and cancel things out. But we are not done when we get to this point because you're dealing with trigonometric functions and there are always little hidden identities when you have squares. Specifically, cosine squared plus sine squared of the same angle is going to turn into the number 1. That's a Pythagorean identity. And that cosine squared minus sine squared is actually another identity. I'll write it off to the right hand side so you remember. This is the double angle identity for the cosine. And actually there are 3 forms of this identity. There's the cosine squared minus sine squared, is what we're looking at right now. But there's also one that's 2 cosine squared of theta minus 1. And there's another one that's 1 minus 2 sine squared of theta. You have to have these committed to memory by this time if you're in a pre-calculus class. If you're in a college algebra class and you're just reviewing this for college algebra, then of course it's not that big of a deal. If you haven't had trig yet and your course doesn't have trig as a prerequisite, you're totally fine. Don't freak out. However, we're going to go ahead and trade out this cosine squared minus sine squared right down here for the cosine of the double angle. Again, once we get to this point, you can actually simplify this a little further. So you're always thinking about how to simplify or shorten the expressions that you're writing down, or the equivalent expressions you're writing down in mathematics. It just makes life easier. And 1 over the cosine is actually the secant. That's just a reciprocal identity. So we have the secant of 2 theta. What's kind of neat about this statement up here is that we were handed something kind of ugly to begin with, and we were able to compress that down into the secant of 2 theta. That's a really neat way of doing that problem. A little heads up though, you do have to kind of be careful when you do this because sometimes the original expression will contain domain issues that your final expression does not exhibit. In this case, actually, both of these, both the original expression and the final expression have the same domain issues, so you don't really have to worry about that. But I'm just letting you know, you do have to watch out for those as you move towards calculus. There are going to be a lot of points in a pre-calculus course or a college algebra course where you're asked to pay attention to the domain of the functions you're working with because they end up causing issues when you start manipulating them. All right, let's go ahead and take another example. Now, I used to do this style of example a completely different way, but since we're talking about simplifying compound rational expressions, I am going to go ahead and treat this problem as if it were a compound rational expression, which it actually is. For years, when I taught this topic, I would do this via factoring, and it is very useful to know how to factor that numerator, but for right now, we're going to go ahead and treat it as if it were a compound rational expression, again, because it is. So let's go ahead and rewrite this term with the negative exponent right here as a 1 over with the positive exponent. Now, when we get down to this point, I just want to pause for a moment to remind you that the exponent, the negative exponent we were dealing with right here, is only attached to the 1 plus x. It is not attached to this x right here. So be very, very vigilant with paying attention to details like that. They are very, very important for us in mathematics. So you only need to move down the factor that the negative exponent is attached to, not the factor where the negative exponent is not attached to. That's why this 1 plus x dropped downstairs. Now that being said, let's go ahead and figure out how to simplify this compound rational expression, basically this fraction containing fractions. All of the other terms within this compound rational expression have 1s as their denominators. So the only thing we have to worry about with the LCD here is the 1 plus x to the 2/3 power. So I'm going to go ahead and grab the numerator and grab the ultimate denominator here and multiply both numerator and denominator by 1 plus x to the 2/3 power. Again, doing that is basically multiplying by the number 1. There is a special restriction here. X cannot be a -1, but to be honest with you, that was the same restriction we had in the beginning. X cannot be a -1 in the beginning because it would have caused division by 0, so we're not adding any level of complexity to this problem by multiplying both numerator and denominator by 1 plus x to the 2/3 power. Distributing this factor to each of those terms there, and then also multiplying this factor or adding its exponent to the exponent of the 1 plus x downstairs, we get the following. Now, if you didn't follow that, it's likely because you need to review your laws of exponents. The laws of exponents tells us that if you have a base, at least one of the laws of exponents tells us that if you have a base to a power p and you're multiplying it, like in this case right here, if you're multiplying that base to the power p by a similar expression with the same base, but just to a different power, we'll call that q, then the result is the base to the p plus q power. Well, 1/3 plus 2/3 is 3/3, or the first power. And that's why that happened there. The other one, obviously, on the second term in the numerator, the 1 plus x to the 2/3 would have canceled beautifully when you attach that to the second term. So that's why that happened. And then we use the same property of exponents, or law of exponents, in this multiplication in the denominator right there. Finally, all you really need to do is clean this up in the numerator and see if something special happens. So we'll go ahead and distribute things through, and we'll go ahead and combine like terms in that numerator. And honestly, there's nothing else you can do with this problem. Now again, I just want to draw your attention to the fact that our original expression, this guy right here, is actually equivalent to this nicer expression. That's the whole reason why you simplify, is to reduce the complexity of the statement. I would much rather deal with this final expression than with that initial expression. And by the way, that initial expression is the result of something in calculus called the quotient rule. So this is something you will have to deal with quite a bit in calculus. And I was about to advance away from this page when I realized that is the last example I have for this material. So in the next video, we'll start talking about how to rationalize numerators and denominators, which is ultimately very important in calculus, just as important as this topic, simplifying compound rational expressions.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.